You know, every single day we're surrounded by this invisible force that tames raw power. It's the secret controller inside your phone, your TV, even your toaster, making them work just right. So today, we're going to pull back the curtain on that force, electrical resistance.
I mean, really think about it for a second. You plug in a toaster, and this massive amount of electrical energy flows into it. So why does it just glow red hot and make perfect toast instead of, I don't know, exploding? What's stopping all that raw power from just running wild? The answer is the key to pretty much every piece of technology we use.
Well, the secret is all in these tiny little components called resistors. They're everywhere, in virtually every circuit. And their whole job is to do exactly what their name says. They resist. They're designed specifically to fight back against the flow of electricity. And this opposition, this fight, is what lets us control electricity with incredible precision.
Okay, so to really get what resistance is doing, we first have to get familiar with the three fundamental ideas that run any electric circuit. You can think of them as the three main characters in the story of electricity: voltage, current, and of course our star for today, resistance.
So first up is voltage. The easiest way to think about voltage is as the electrical push or pressure in the system, right? Just like water in a pipe needs pressure to make it flow, electricity needs voltage from a source, like a battery or wall outlet, to get it moving. It's the force that gets things started.
Next, you've got current. So if voltage is the push, then current is the actual flow of electricity that happens because of that push. It's the moving charge that does all the work, powering the motor, lighting up the bulb, or heating the element in that toaster. And we measure this flow in amperes, or just amps for short. And that brings us to resistance. This is the opposition to the flow. It's the measure of how much a component fights back against that current. Simply put, resistance is what slows electricity down, and we measure it in a unit called the ohm, which is represented by that Greek letter omega. The concept itself is actually pretty straightforward. A material with low resistance is kind of like a wide-open six-lane highway for electricity. Current just flows through it super easily. But a component with high resistance, that's more like a narrow, bumpy country road. It really restricts the flow. And that ability to control the flow, well, that's everything. So we have the push, the flow, and the opposition. But how do they all connect? It turns out there's this beautifully simple and incredibly powerful rule that links them all together, and it's basically the foundation of all modern electronics.
See, these three things aren't independent. They exist in this perfect mathematical relationship. It's so predictable that if you know any two of them, you can always figure out the third. It's elegant, and it's the bedrock of all circuit design.
And this relationship is called Ohm's law. It's like the secret code for every circuit. The formula is really simple. Voltage equals current times resistance. This triangle here is a fantastic way to remember it. You just cover up the thing you want to find, and it shows you exactly what calculation to do. So handy. It really all boils down to this. How much current you get in a circuit is decided by just two things: the voltage pushing it and the resistance pushing back. That's it. It's a direct cause and effect relationship that gives engineers total control. Okay, let's look at a really quick practical example. In this circuit, let's say we measure a voltage of 4 volts and we see a current of 5 amps flowing. Using Ohm's law, we can figure out the resistance. So resistance equals voltage divided by current. That's 4 volts divided by 5 amps, which gives us a resistance of 0.8 ohms. It's really as simple as that. All right, so now that we've got the rule book, let's see how it's actually used out there in the real world. We can basically categorize every material on Earth based on how well it resists electricity, which lets us harness it for all sorts of things. So when engineers are designing circuits, they don't draw a picture of that little component. They use a universal symbol, this simple rectangle. It's the visual shorthand for, we are controlling the current right here. So materials pretty much fall into two camps. You've got conductors, like copper and other metals. They have really low resistance, which is perfect for wires. Then you have insulators, like the plastic or rubber around those wires. They have incredibly high resistance, so they just stop the flow of electricity dead in its tracks. And that, of course, is what keeps us safe. And get this, a material's resistance isn't always fixed. If you take a wire, for instance, a longer wire will have more resistance than a shorter one, and a thicker wire has less resistance than a skinny one. It's just another layer of control that engineers can play with.
Okay, so we've covered the what and the how, but let's wrap this up with the most important question. Why does any of this really matter? Why is this invisible fight happening inside our electronics so incredibly important?
Here's the bottom line. Resistance is what makes electricity useful. Without it, we just have raw, untamed power. By adding resistance, we could dial the current way down for a delicate microchip. We can use it to generate heat in a toaster or light in an old-school light bulb. Resistance is the ultimate control knob.
This leads to a really fascinating question, right? We absolutely need resistance to control electricity, but at the same time, it causes energy to be wasted as heat in places like power lines. So, is it a good thing or a bad thing? Helpful or harmful?
And the answer, of course, is that it's both. It's a constant balancing act. The very same property that toasts our bread also wastes energy on the power grid. And the entire challenge of electrical engineering, the very thing that makes our modern world possible, is mastering this duality. It's all about learning when to fight the flow and when to just let it run free.